let's find the definite integral here in two ways. We're going to do it using the fundamental theorem of calculus part 1, in other words, the definite integral. We're also going to do it finding the signed area between the curve and the x-axis. All right, here I go. Boom. Antiderivative of 2x is x squared. Now, some of you might be thinking, don't we need the plus c? Go ahead and put the plus c and see what happens when you finish. All right, but I'm not going to put the plus c. We'll talk about why in a minute. So, vertical line is the notation that we often use. Sometimes you'll see notation like that, like a bracket, after you've taken the antiderivative. You'll see both of these, but more commonly the vertical line is used. All right, and since the definite integral, remember, is the displacement or the change in your amount, it's always the end minus the beginning. So I'm going to put in the top number first. Why did I put a negative there? The top number first minus -1 squared. Okay? So I have 4 minus 1, which is 3. That's my definite integral. Remember, a definite integral is a constant. It's a value. It's a number. Okay? Hey, those of you who tried this with a plus c, what happened at this phase when you had the plus c? If I had a 2 squared plus c minus -1 squared plus c, all those plus c's would subtract each other and become 0. So that's why when we're doing definite integrals, you can dispense with the plus c. All right, we have a definite integral of 3. If this were a velocity function, this would be my displacement from -1 to 2. A little weird talking about -1 time, but you know what I'm talking about. All right, let's look at the graph. I just graphed 2x. The definite integral is the signed area between the curve and the x-axis. So I'm going from -1 to 2. I'm going to just shade in that area. I hope you're thinking what I'm thinking. This area is underneath the x-axis. So that's going to be negative signed area. This area is above the x-axis. That's going to be positive signed area. If this were velocity, right? If my velocity were in negative land, I'd be moving to the left. If this were a velocity function, 2x, now I'd be moving to the right. So this all makes intuitive sense. Let's actually find the area of that triangle. 1/2 base times height, so I think that's going to be a -1. This is 1/2 base times height, so that's going to be a, let's see, 2 times 4, that's 8, so that's a 4. So I have 4 plus -1, which is 3. Bingo, bango, those match. So the definite integral is signed area. You can think of it as displacement or the change in the amount. End amount minus your start amount. All right, let's do a couple more examples. What if I wanted to find this definite integral? Well, the first thing I'm going to do here is to rewrite this and think of this as x to the 1/2. And now I like just thinking, what has a derivative of x to the 1/2? Well, x to the 1/2, I'd be, if I were doing something like this, I'd be using the power rule. So it's kind of like I want to undo the power rule. The power rule, if you recall, you always subtract 1 from the exponent. So I think I'm going to add 1 to this exponent. Let's see, a handy form of 1 is going to be 2 over 2. So that's going to be x to the 3/2. Are you with me here? So let's check this. Let's take the derivative of x to the 3/2. That would give me 3/2 times x to the 3/2 minus 2. Oh yeah, the exponent is right, but I don't want a coefficient of 3/2. What would be a handy thing to multiply 3/2 by to make it go away, to turn it into a 1? You're right. 2/3 is going to work. Okay, fantastic. Now, if I were doing an indefinite integral, I would write a plus c and I'd be done. But I'm doing a definite integral, so I'm going to do my little vertical line. I'm going to put a 4 here and a 9 here. And continue. Remember, it's always the top minus the bottom. It's the end of your interval minus the beginning of your interval. All right. If you have a calculator, you can just go ahead and do this in your calculator, but that's kind of no fun. Let's do this by hand. The 2/3, I'm actually just going to factor that out. I'm going to think of this as the square root of 9, and then cube whatever I get, minus the square root of 4, and then I'm going to cube that. Let's see, the square root of 9 is 3. 3 cubed is 27. The square root of 4 is 2. 2 cubed is 8. So my answer is going to be 2/3 times 19. All right, that's not that bad. Or 38/3. Remember, a definite integral, you always get a number, a value. Now, just for fun, if you wanted to graph that thing, right? Let's go ahead and graph it. Square root functions look like that, and you went from 4 to 9. Well, that would be hard to find that area using geometry. All right, we kind of need calculus to find that area, but you can at least visualize it's all in positive land, so all of that area happens to be positive. Okay? Let's do one more example. All right, finding the definite integral. So you might say, well, what's that 2 out there? Well, that's just a coefficient. And whenever you have a coefficient in front of a function when you take the derivative, remember the coefficient just hangs out and is multiplied by your derivative. It's like a scale factor, right? Same thing here. If you have a coefficient, it's just going to be multiplied by your result that you get from your definite integral. So let's think to ourselves, what has a derivative of cosine? Oh, that's sine. Okay, that's not that bad. So the 2 is going to hang out times the sine of theta, analyzed from 0 to pi. Okay? All right, so here I go, 2, I'll just put that up front, sine of pi minus sine of 0. Well, this isn't that hard. Sine of pi, that's just 0. 0 minus 0. Oh my gosh, that's just 0. Isn't that interesting? Well, wait, why would that be? How is that possible? How is that possible? Let's think of, I mean, it seems like there's a lot going on. How could my displacement be 0? Well, let's think about what a function of cosine looks like. Cosine starts at 1, then goes down, and then goes back up, and blah, blah, blah. And let's see, this is 0. Oh my goodness, I think I'm starting to see it. There's pi. So if I were looking at my signed area, knowing what we know about cosine, it's going to be, right, a nice kind of rotational symmetry there. This positive signed area is exactly equal to that negative signed area, so that makes sense that we ended up with a displacement of 0, or a change of my end position minus my beginning position of 0. So I think these definite integrals are fun. I hope you do too.